Be talking about this AES-ECB crypto CTF challenge I did. Start off, who am I? I'm Chase. I'm the head of research if you haven't known. I'm from Long Island. I'm like a second and a half year at this point. Like music, surfing, bagels. I try my best, and I have a qualified medicine CTF under my belt. But for this presentation, who I actually am is a noir detective from the 40s. So today we're going to be investigating this challenge. We're going to be covering the challenge, the theory, the technique, and the solve. So let's just jump into it. To start off, the challenge goes as, oh no, I ruined the tux. Oh no, I spilled AES all over my friend Lunkbow's copy of tux. Can you help me recover the original image for him? I found an old backup and some contact information about some Oracle thing if that helps. The files are here, and the contact information is localhost at lead, or however it was hosted on the site. This is the crime scene. You have the encrypted image of tux that AES was so fortunate spilled on. So if we compare this to the other backup image that was compared, as you can see, you can kind of tell that there's an outline in this image. This is because of the AES-ECB mode being kind of deprecated and bad at encrypting. As you see, it copies every couple lines. And also, there's this other little line of black if you compare it to the normal image. As you can tell, they did not use a high-res image. This one I pulled from Google is a lot nicer looking. But as you can see, there's a small bit here. If you enhance, you can see that it kind of looks like binary. And if you see the top line looks fine, the middle line looks like it was tampered with, and the bottom line looks fine. So if we decrypt that, you see again, you have the flag wrapper and you have N and a bunch of these weird Ys. This is purposely done, purposely obfuscated so we can't see it. And these are the flag bytes. And this is in the backup image. The encrypted image has the original ones, but encrypted. So if you want file on this, as you can see, it is a weird image file that you probably haven't seen ever. It is a NetPBM image. It's a PixMap. It basically is just another way to store data. As you can see, it starts with this P3 header, has some comments. It's a 3x2 image, and this one uses ASCII color values, so that's why it prints out red, blue, green, or red, green, blue, RGB. And it's basically just another way to store values, similar to it like a JPEG or a PNG. So if you look into some deeper secrets, you can tell that the image is 256 by 304, that is stated in the file. If you open it up in like a text editor, it shows that, and all these random jargon bits at the bottom at a later point too. And it is P6 at the top, so that is byte encoded. B has these RGB values, so it's 3 bytes for each pixel, and it is 96 pixels down. If you open it up in GIMP, it shows you that. And some helpful resources during this investigation was Filippo Valsorda. He has a good article on the encryption process, which first takes the original image into a PPM with GIMP. This is based off the original famous image of tux that was encrypted using this way. You take that top header apart, you do a little head into another file, you take the body, put it in another, encrypt it with ECB and some different keys. They used ANA, they did OpenSSL, AES 128 ECB. 128 uses 16 byte blocks to encode. That's why it repeats every 16 bytes, not 16 pixels. And then it takes that, puts it back together, and then makes that image. Another part of the challenge was that Oracle. At the start, it said the contact information is localhost with the port, whatever that means. If you connect to this port using something like Netcat, you can see that it prompts you with, welcome to the Oracle. Ask me your question and I'll consult the Oracle. Don't worry, I'll pad your question if it's small. And I entered hi, the Oracle spoke, and a lot of random bytes that do not directly translate to ASCII. And it prompted to ask again. So if you ask the Oracle, you shall receive. This can be determined to be the encryption that was used to encrypt that original file. So this is what we're going to be used in the solve. So another question, if I ask it, what the scallop? It had trouble with that question. That's because what the scallop is 17 bytes long. You might be like, what space the space scallop is 16? But if you send it using that cat, it comes in with a new line character at the end, which is another byte, which is why it has trouble. It works if you do 32 bits, any multiple of 16, it knows how to pad. And if you go less than 2. So some other facts that we can take away are the possible chosen plaintext attack on this, a block cipher, which is the type of cipher that it is, general PPM information. Crypto Stack Exchange was very helpful when researching this. There's a lot of people that know a lot more about crypto than me. So some interesting things that found were that it was made using AES-ECB mode. It had these 16-byte blocks that were repetitively encrypted. It was a PPM file. It has some plain text shenanigans, which we can abuse. We have the Oracle encryption, and we know that it is 256 by 304, and it's 96 pixels. 256 and 304, those are both divisible by 16. So that leads into the theory behind it. Theory, so to start, we can tell that byte header is 16 bytes. It is P6, it's byte encoded. It uses GIMP to do it, that's meaningless. Some plugin, and it's 256 by 304, and then that's like a starting byte of 255. It's integral for how we're going to solve this. So we can also understand the pixel size a little bit more. You have 1 byte for each value. It'll be 255, 255, 255, and that'll equal the RGB values for 1 pixel. So that kind of isn't so good because 3 times 5 is 15. So in order to do some of the shenanigans that we have to go to 16, and that will cause us some problems later. Furthermore, we have the flag length. This is the flag. It's just the first one decrypted is the letter N, and a bunch of random ones obfuscated. So these are 8 times 10, 80 bytes. 80 bytes is the length of the flag. So how we're going to do it is bring this all together. We realize that we can build a cache using the Oracle, basically having a map, mapping every possible encryption versus comparing that to the encrypted bytes of the file. And then using that, we can rebuild the flag after. So this is how we're going to start. This is the values that we have. We have 240 is the flag length. We have the IP in the port, how we're going to connect to the Oracle. We have the flag start that we know starts at 61. And after some complicated math, taking 256, the length, times 96, byte down, times 3 RGB values for each pixel, plus 21 to push us past the other random jump, then we can just jump into it. And we can talk about the technique of how to actually solve this. This involved quite a bit of coding. So to start the program, we have our variables declared, we have our flag start, and we have the start of the test. So you have this tux intent file that we start reading in bytes. We seek up until the start of those bytes in the data in the file, and then we read the flag length amount. And then we import iter tools to start building our cache. This pixel values are x, FFF, FFF, FFF. This is the values for the white pixel. And for the black pixels, it is 02, 02, 04. Usually like a pure black pixel will be 00, 0000. But if you actually eyedropper the image, you can tell that the hex values are different. This adds another layer of stuff that we got to mess with in some edge cases. But right here, we repeated 6 times. Because as I said, 3 times 15 is not 16. And so we have to multiply it and then cut off the edge, leading to those garbage edge cases. So initially contacting the Oracle, I'm using something called Pwn Tools. This basically does Python sockets but better. And we connect to localhost on the port. We receive until it prompts us about the Oracle. We send in a message. We receive until it sends a message, and we ingest that. So that's how we're going to talk to the Oracle and start building the cache. Pwn Tools, lovely. And we do a little strip here to clean up some of the garbage that the Oracle spits back at us. And for the edge cases, this is a little messy. So because the black pixel does 2, 2, and 4, there's a lot of different ways that we can interpret 16 bytes, mainly because the 2, 2, 4 can be the last one, the last bit can be 2 and 4, the first one can be 2, 2, the third one can be 4, or it can be split in the middle. This is quite gross. And then the code that we have to solve this, basically just for each of our guesses, we join and we do a little slicing, cut off the edge, and just add those all to the cache. These are just, they're so simple. They're so simple. And now to actually check the check against the cache, we take our encrypted flag bytes, we go over every 16 bytes, we slice, we check, and we concatenate to our decrypted flag bytes. And then we check the cache, and then we can figure it out. We don't have to care about the pixel integrity here because we've already handled that. And this is what the output is. That is gross. You can probably do this manually. You may even be able to throw this in CyberChef. But the way I did to fix the output is create a little pixels to binary function, which just looped over, checked if it was 255, 255, 255, or 224, and then just added 0 ones to bring it back to the binary that was encoded in the original image. And now, to solve, finally, we've taken long enough. But if we check, I have a little GIF here of running this Python program. As you can see, I will be using TQDM. It makes such a nice progress bar. This was so helpful. This is the only thing that kept me motivated through the way too long of time that it actually took. This is in live time, by the way. It really takes this long. And the output is the flag image encrypted in binary. So if you wait just a second longer, boom, it outputted. Lovely. And the flag ended up being decrypted as not as soup. So that is the flag. And it actually worked. It did not work this easy the first time. It was a lot of struggle, a lot of thinking, a lot of looking at articles, things like that. But now we need to find who the culprit is behind this challenge. So as we can tell, the wrapper was not shown in this presentation. The IP is localhost and leap. That's kind of suspicious. And it's quite an interesting challenge. I don't know who would make this besides myself. I made this challenge. Thank you. Are there any questions?
So I just have in this scenario, if you really needed to talk to the Oracle, but the Oracle is locked behind a physical lock of some sort, how would you get through that physical lock?
If only I had some tools to pick that lock.
It is Chase's.
Oh my god. It's 7th presentation and smile. Wow, for the stream.
There you go, buddy.
Oh my gosh. You were gonna do that? Maybe you should have been here on time then. Laser pointer. Are there are there any questions about the presentation at all? Well, thank you. These are the slides I used. Let's go.